Integration by parts is a method of integration used when the integrand consists of a product of two functions. Before we get into any example problems, let's take a look at how this formula is derived. Let's start out with the product rule and apply it to the product of functions u and v. We find that that equals du dx times v plus dv dx times u. We can cancel out the dx's from each of the denominators and rearrange the terms so that we get u dv is equal to duv minus v du. And then we take the integral of both sides and we get the integral of u dv is equal to uv minus the integral of v du. Once we're at this point, we need to decide which function in the integrand is to set equal to u and which to set equal to dv. And then once we do that, we need to find du and v so we can have all the terms to plug into the formula. Finding du is relatively simple. You just take the derivative of the function and multiply it by dx. However, finding v is a matter of deciding what function to set as dv. We want to make sure that the function that we choose to represent dv is easier to integrate than the function that we choose to set as u. A good indicator of which function in the integrand to set as dv is to look at what kind of function it is. You can look at this acronym called detail, with d representing dv since we're trying to find what kind of function is optimal to set as dv. The rest of the letters represent types of functions in order of highest priority to lowest priority to set as dv. That means if there are different functions, one exponential and one trigonometric, you should choose this exponential function to set as dv, because an exponential function such as e to the x is inherently easier to integrate than a trigonometric function, since the integral of e to the x is simply e to the x. And if you have a trigonometric function and multiplied against a logarithmic function in the integrand, that means you should choose the trigonometric function to integrate and set as dv rather than the logarithmic function. Now let's take a look at some example problems. This one will be the easiest one out of the three I'm bringing up in this video. Let's find the integral of x cosine x dx. The first step is finding which function, x or cosine x, to set as dv and which to set as u. So let's take a look at detail. We can visibly see that trigonometric functions are ahead of algebraic functions due to the order of the letters in this acronym. So that means trigonometric functions hold higher priority to set as dv. So let's just set cosine x as dv and x as u. Now we need to find du and v. Du is just the derivative of x times dx, so that's 1 times dx. And v is the integral of dv, which is cosine x. The integral of cosine x is sine x. So let's plug in these terms that we now know into the formula. Just as a reminder, the formula is the integral of u dv is equal to u times v minus the integral of v du. Plugging in the terms that we now know, u is x and v is sine x minus v sine x, and du is equal to dx. This is a pretty easy integral to take, since the integral of sine x is just negative cosine x. So when you take the integral and distribute the negative, you get that x sine x plus cosine x plus c, since this is an indefinite integral, is equal to the integral of x cosine x dx. Let's take a look at another problem, this one of medium difficulty. Let's find the integral of x squared times e dx dx. First step is always to find which of these functions, e to the x or x squared, to be set as dv, and the other will be set as u. Let's take a look at detail, but since it's not on this page anymore, let's just try to remember it. E to the x is an exponential function, and x squared is an algebraic function. Exponential functions have high priority to be set as dv over algebraic functions according to detail, so we'll be setting e to the x as dv and x squared as u. Finding du is just a matter of taking the derivative of x squared, which is equal to 2x, and multiplying by dx. And finding v is taking the integral of e to the x, which is still e to the x. Now that we know all the terms that are in the formula, let's write out the formula and solve. Remember that the formula is equal to u, or the integral of u times dv is equal to u times v minus the integral of v du. And when we plug in the terms that we now know, we can get that x squared e dx minus the integral of v du. V is e to the x and du is 2x dx. Look at this integral over here. We can't integrate it normally, and we actually have to apply the integration of by parts formula once again, this time to this integrand. So we'll have a new set of u's and v's and dv's and du's. And for ease, just consider the dv I set in this equation and the u that I set in this equation completely separate from the ones that I already set previously. Once again, e to the x, an exponential equation, is higher priority to be set as dv according to the detail acronym, since 2x is an algebraic function. So we'll be setting e to the x as dv and 2x as u. Du is the the derivative of 2x times dx, so that's 2 dx, and v is the integral of e to the x, which is equal to e to the x. Let's plug these terms into the formula. So this is equal to u times v, 2x times e to the x minus the integral of v du, e to the x times du, 2 dx, 2e dx dx. 2e to the x dx is integrable through normal means, since 2 is a constant and the integral of e to the x is just e to the x. So let's evaluate these terms. Minus 2e dx plus c. And we can distribute the negative. Notice that c always remains, or the function before c is always plus. Since c is a constant, it's pretty arbitrary what it is. So it can be a negative value, but for convenience sake, we'll just keep it positive from now. So we end up getting that the integral of x squared times e to the x dx is equal to x squared times e to the x minus 2x times e to the x plus 2e to the x plus c. So what can be taken away by this problem, or from this problem, is that the integration by parts formula can be applied multiple times, so that each resulting integral by applying the formula can be solved. This is the last and most difficult problem. Let's find the integral of e to the x times cosine x dx. So first step, as always, is finding which of these functions, e to the x or cosine x, to set as dv, and which one will be u. E to the x is an exponential function, and cosine x is a trigonometric function. According to detail, exponential functions take higher priority to be set as dv than trigonometric functions since they're easier to integrate. So we'll be setting e to the x as dv and cosine x as u. Finding du is a matter of taking the derivative of cosine x and multiplying by dx. So we get du is equal to sine x dx. And finding v is done by taking the integral of e to the x, which is equal to e to the x. Once again, let's just write out the formula so that we know what we're doing before we plug terms in. Integral of u times dv is equal to uv minus integral of v du. So u is cosine x and v is e to the x. So uv is equal to e to the x cosine x. I'm ordering this so that we can keep the order standard throughout doing this problem. And minus integral of v du. V is e to the x and du is negative sine x dx. Minus the integral of e to the x negative, or the integral of negative e to the x sine x dx. So we can just take out this negative, and what we can see is that, once again, I think we need to do the integration by parts formula once again. So we can set, well, we need to determine which of these functions to set as dv. And remember, whenever you do, or you're forced to do, an integration by parts formula multiple times in a problem, just remember that whatever you set as u and dv for each step is separate from the other steps. So according to detail, the exponential function e to the x is of higher priority to set as dv since sine x is a trigonometric function. So we can set e to the x as dv and sine x as u. Finding du is a matter of taking the derivative of sine x and multiplying by dx. So you get cosine x dx equal to du. And finding v is a matter of taking the integral of dv, and that's the integral of e to the x, which is equal to e to the x. So now that we know these terms, we can plug them into the formula another time. Plus u times v, so sine x times e to the x plus e to the x sine x, minus the integral of v du e to the x times cosine x dx. It seems like since the integrand each time we get a resultant integral by applying the integration by parts formula, seems like it can't be integrable, and we might just have to use the integration by parts formula on and on forever. But look at this. The original expression was the integral of e to the x times cosine x, and it reappears here. So what we can do is set this original integral is equal to I, and we can say that I is equal to this expression right here. So I is equal to e to the x cosine x plus e to the x sine x minus and this expression is I, so it's minus I. We can move and isolate i's on this side, and 2i is equal to e to the x cosine x plus e to the x sine x. We can divide both sides by 2, and we get that the integral of e to the x cosine x dx, which is equal to I, is equal to 1/2 e to the x cosine x plus sine x. So the first or the second example, we learned that we can use integration by parts multiple times. But we don't really want to go too far with that. So once we can recognize in certain cases that the integrand is, or the resulting integral by applying the integration by parts formula is actually equal to the original integral that you're trying to solve, you can use this method and it'll save a lot of strife, and you won't have to use the integration by parts formula a couple million times. So that's it for this video. I hope you enjoyed.